I'm a developer on the SecDB team in Goldman Sachs. Today I will be talking about how we're trying to use Oracle's GraalVM to incrementally modernize the implementation of our proprietary scripting language, which we call Slang. I'll be talking about some of the challenges we faced because we're taking this incremental approach. You're unlikely to see an incremental approach in many projects because most people just re-implement a programming language from scratch. But before that, I suspect some of you are thinking, am I not a little young to be speaking at Curry on behalf of Goldman Sachs? Yes, I am. You can read my bio online, but the gist is I'm only a recent graduate hire. At the end of this month, I will have finished 1 year at Goldman Sachs. I'm speaking on behalf of a pretty wonderful team. Zach is the lead for this project. Jackie is the lead for SecDB as a platform, and John is the lead for SecDB globally, which includes cloud and data as well as the platform side of things. So first I need to tell you in, I'd say about 60 seconds, what the hell SecDB and Slang even are. So this quote is taken from an internal article written about SecDB. SecDB is short for Securities Database, though nobody really says that anymore. It started off for life as a pricing and risk platform. And it's about 26 years old now. To put that into context, Linux, Standard ML, Haskell, Python, they were just kind of infants at the time SecDB was created. Java and OCaml didn't even exist yet. It's shrouded in a bit of secrecy, but you can search for it online. There are a few good articles you can find out, used to find out the impact it's had on Goldman as a firm. And it's still really important to the company. But that's kind of answering what SecDB is used for. It doesn't really answer what SecDB is as a thing. But it's kind of a platform, so it's many things to many people. It's a platform which was, at its inception, really sophisticated and very much ahead of its time. It's also a platform which started off as an open code base with people hacking on it like crazy. So it's accumulated a lot of features and more than its fair share of technical debt. But today I'll be focusing on the main way that platform is used, which is Slang. It's a full-featured scripting language for defining calculators, building applications, creating reports, and more. By more, they mean like everything. We have games written in Slang, we have a Secret Santa organizer, and even a piano app, if you can believe that. But I hear you say, what is Slang? Now, before I continue, I want to briefly describe Goldman Sachs' love-hate relationship with Slang. Slang's biggest strength and weakness is that even after about 26 years, it still basically works. That too with much less investment in it than other languages you can name. Think about it. If it didn't basically work, I wouldn't be up here. We would have been forced to replace it ages ago. However, I wouldn't be painting a realistic picture if I said that there weren't any flaws with it. It's really good at some things, and it's really not so good at others. There are several good features about Slang, but there are also several technical decisions which 26 years later, and with the benefit of hindsight, we can say, oh, that was definitely a bad idea. But this should not be taken as a criticism of the people who made those decisions, because, at the time, with the context, it might have been a fair point. So this is what Slang looks like as code. This function is just a random one that I selected from a utility script. It's called UT Secret Santa, to give you a feel for the aesthetics of the language. The exact syntax and semantics are not important for this talk. Slang is a gradually typed scripting language. It is single-threaded. It's syntactically somewhere between C and Lisp, which is really weird when you think about it. It has no reserved keywords. Identifiers are case insensitive, and they can contain spaces, which is super that blew my mind when I first saw it. It's either you love it or hate it, but you get used to it. And it's interpreted with a tree walk. So the abstract syntax tree, the AST, it can be and sometimes is manipulated at runtime. If you know anything about implementing programming languages, you'll know why this Picard is worth it. Anyway, continuing on. Slang is implemented through C-style message passing. The set of primitives available to slang can be extended using what we call slang add-ins written in C++. We have these things called UFOs and type structures, which provide some object-oriented features. And combine that with higher-order functions, you can choose to write slang in a procedural, object-oriented style, or functional style. In my opinion, this is just me, what I think personally, slang is most similar to self semantically, not so much for the prototype-based hierarchies, but for the message passing style implementation, the ability to redefine almost anything at runtime, but it's got a healthy influence of Lisp in there too. Slang never had any sort of specification or investment comparable to that put into other languages. It's evolved over time to meet the needs of its users. So its list of features is kind of this expected hodgepodge of ideas people thought were good at the time. So when I describe slang to people, I often get asked a fairly similar set of questions by people who are new to slang and SecDB. If you want to know more about the history of slang and SecDB, how we got into this situation, why we're not using Python, I suggest you look for a talk with a similar title to this one that Jackie and Zach gave last November at the Oracle Code 1 conference. Wait for it. Currently, we have more than 150 million lines of slang code. When I made this graph, it was around 157 million lines of code. This is critical data, libraries, applications running in production. These are all written and deployed in a huge, large, interactive, and dynamically updated environment. You can push a change to a script, and in seconds, it is picked up all around the world by everything that uses it. If you want to know more details about this environment, please ask me at the end. I'm happy to describe more about it. The code for slang is a 26-year-old monorepo. It contains 350 primitive types and thousands of quote-unquote built-in C++ add-in functions. We have about 10 million lines of these add-ins. All these add-ins make some sort of assumptions about the abstract syntax tree and the interpreter, which is the precise reason for the Picard facepalm earlier. So not using slang is not really an option at this stage. The best some teams manage is to minimize their use. And because of the wide base of add-ins and types, splitting it up into, say, a services-based architecture is a non-trivial long-term project. It will be a while before we see the results of any such effort. Now, the academically inclined of you might be thinking of the Essence of JavaScript paper by Guha, Saptayu, and Krishnamurti. In it, the authors express the entire JavaScript specification in terms of a very small, formally defined, easily understandable calculus they called lambda.js. So could we conceivably do something like that for slang? I personally don't think so, at least not at this stage. The reason is, in the case of slang, it's not a simple reference or a specification. It's just kind of what the interpreter decides to do. Combine that with the base of 350 types, 10 million lines of C++ add-ins, it's just unlikely that there's some elegant core underneath it all, in my opinion. We could compile a subset of slang to, say, Lisp or assembly, but both have already been tried, and the latter has also become an extra maintenance burden of really brittle code. Now we have N+1 languages, it doesn't get rid of the existing slang, and it's not ideal. While simplification of the language is something we want to do it gradually, over time. Cutting out any subset of the language, or having a sharp version 1.2 boundary, you can think of JavaScript and use strict, or Python's version 2 and 3, that's an unappealing option to us. Rewriting the entire interpreter from scratch is also difficult because of all those add-ins and the assumptions they make. Also, that assumes we can replicate the semantics of the language exactly, including all the bugs. And I shouldn't need to point out how unlikely it is to achieve that. We did also consider compiling to Python or JavaScript. In fact, one day I found a slang to Lua translator written in slang, which is used in production. But that's also really hard to get right. You know, amongst other things, slang has a very strange type hierarchy. So messages such as value A is a type of type B, or type C is a base of type D, don't map cleanly onto the type systems of other languages. It's also an unappealing option if we want to aim for readable code. None of these ideas that I mentioned are inherently impossible. But given the engineering effort they require, something on the scale of something like Hack, V8, BuckleScript, and the fact that they're all kind of big bang approaches, it would be a really long time before we saw the fruits of any of those efforts. They're all kind of high risk, high reward, all or nothing endeavors. So what would be really ideal is an incremental approach to improving our interpreter, and that's where GraalVM comes in. Of course, we would love it if we could re-implement the entire thing from scratch, and doing it incrementally is actually posing some interesting challenges that we wouldn't have otherwise. Graal is a new JIT compiler for the JVM. Truffle is a framework for implementing language interpreters which take advantage of Graal. Sulong is an LLVM bitcode interpreter written using Truffle. Substrate offers native compilation of Java applications, such as an interpreter written in Java. It's an impressive bit of tech, and it's been used to develop many implementations, many fast implementations of dynamically typed scripting languages, such as Python, JavaScript, R, and Ruby. Please make sure you're familiar with these terms, because they're going to come up in the talk a lot. So we started off phase 1 of this project to see whether or not GraalVM could even work for us at all. Picking up from where Jackie and Zach had left off, we'd concluded that slang could work. We could get existing core data types and interop with the interpreter. We liked the tooling that we got, quote unquote, for free with the profiler and debugger for slang. And the resulting code was fairly easy to understand, maintain, and implement. So these were all positives. However, we had one remaining question, which was, can we surpass existing performance? How did our Truffle interpreter work at the end of phase 1? How did it allow us to work incrementally? Well, first, we used the existing native C++ parser to get an abstract syntax tree. Then we take that AST and we recurse over it on the Truffle side. If we see a node whose functionality we have re-implemented on the Truffle side, then the Truffle slang interpreter can handle that. Otherwise, we wrap it up in such a way such that it delegates back to the existing interpreter. The reason any of this works at all is that we moved the variable stores over from the native side to the Truffle side. And we also exposed an API for manipulating that variable store back to the native code. So this means both code on the native side and on the Truffle side can manipulate variables in the environment. And the variables environment lives on the Truffle side. Once the lifting is done, the Truffle slang interpreter kind of takes over and it produces a result, something of type DT value. DT value is the type of runtime values in slang. The code on screen implements a slang if expression in kind of exactly the way you'd expect it. First, you evaluate the condition, and depending on the result of the condition, you return the result of evaluating either the true branch or the false branch. Kind of big step semantics in code. So as I said earlier, we need variables to be handled by and accessible to Truffle. The diagram on screen, it shows in a bit more detail the API for reading a variable by name and scope from the native side, and you can see the chain of events, and particularly this one in the middle called the variable access VM boundary is where you have a crossover between native code and quote-unquote Java code. Calls to native C++ from the Truffle side work in the same way, but they go in the opposite direction. There are a couple of extra steps we need to take. First is we need to have memory allocated for the result of the native call. And then we need to also have the native call available to the runtime. By the way, the native calls that I've been talking about, they're not done manually via the traditional JNI that you might be familiar with. This native interop is handled by the LLVM bitcode interpreter Sulong. So you compile some C++ code to LLVM, Sulong takes over, and if there's a code or a call to native code from that, Sulong handles all the quote-unquote magic at that point. We can also use the substrate's native function interface for handling the interop. So after phase 1, we felt kind of cautiously confident that Truffle slang could work. So now we moved on to phase 2, which is, can it be faster? The main performance bottleneck is interop overhead. Things are good if you stay on the Truffle side, and they're no worse than currently if you are using the native interpreter. But anytime you have to go between the two, you're in for a world of pain if you use the bridge interpreted using Sulong. So there are two broad things you can do about this. The first is you can minimize the number of times that you cross the native Java boundary. You can lift more functionality into Truffle. That's almost obvious. Or you can use the specialization features to remove unnecessary calls back into native. We'll see how this works in just a few moments. The second thing you can do about the interop overhead is change the boundary. And this is, when we realized this, it felt a bit sneaky. What do I mean change the boundary? Right? Currently, at the end of phase 1, we had something like this. You can either move the boundary, so you can compile more of the existing C++ code onto Sulong, or onto LLVM and run it using Sulong, so that more of the existing native calls, so to speak, stay within the Java land, like so. Or what you can do is move the boundary completely the other way, and that's used by using Substrate, so you have native compilation of Java applications. We've already covered how lifting functionality works, so I'm going to focus on specializations now, and we'll be covering on the difference between the boundary adjustments in our evaluation. If you haven't heard of specializations before, I highly recommend this paper. It talks about how specializations were implemented for the Self programming language. This programming language was hugely influential and pioneering for JIT compilers such as JVM, LuaJIT, and V8. But to give you an intuition about specialization, let's look at a small amount of code. All this code is doing is starting off with an empty array, and on each iteration of the loop, we're appending the size of the array for that iteration, and we're returning the size at the end. So at the end of this program, we'll have an array with 100 elements from 0 to 99. We, as the programmer, know that throughout this whole program, X is pointed to an array. We also know, in two other cases, that the ampersand equals, or the append message, is for an array, or sent to an array, and the less than or equal to, or sorry, the less than message is sent to the result of size X, which we know returns a double. However, the language doesn't know this. It does a full general case message passing every single time. So this is how we would express something like specializations for the size message in Truffle. I've omitted some details for the sake of fitting the code on the slide, but this is basically telling Truffle that there are two receivers of the message size. One is a regular Java list, and the other is a DT value from the existing interpreter. In the first case, all we need is the list, and we return the size of the list or array. It's a double because, like JavaScript, we don't have integers. In the second case, we not only need the DT value, which represents the array to which the size of this message is sent, but also the memory or the object to hold the value of the result, and an object which represents the FFI call to the native code. For the sake of space, I've omitted how we, as programmers, tell Truffle to how to find the last two arguments. These are done via annotations. What's really worth paying attention to is how a specialization can eliminate a boundary crossing in this instance. The code on top, it doesn't use any boundary crossing. It just stays within the Java world, and it can be optimized and jitted quite nicely because of this. The code on the bottom, however, needs to make the jump back across. And basically, we have the same deal here, but this is with append instead of size. We're either appending a double to a list and returning that list, or we're appending an arbitrary DT value to another arbitrary DT value and returning result as well. If we do this wrong and we miss a case for a specialization, then we'll get an exception, such as an unsupported specialization. So now we can talk about what we found out in terms of performance results. Let's start where we left off at the end of phase 1. This is the Truffle interpreter with the bridge interpreted in Sulong. Smaller numbers are better. I'm only going to show numbers for one benchmark that we did. This is the Spectral norm benchmark from the computer benchmarks game. It only tests a small subset of slang features, mainly number crunching with arrays. But we had a few other tests, but Spectral norm is fairly indicative of the other ones, so for the sake of simplicity in this presentation, only going to show this one. And we kept an eye on the errors, standard deviation. All the numbers with the Java are after the Java JIT has been warmed up, or the Graal JIT specifically has been warmed up. On the left, we have three languages. First is Python, then Java, lastly Slang. And we can see that Slang is about 10 times slower than Python. Please remember that the absolute numbers are not so important, but the relative ranking is. So first Java, then Python, lastly Slang. But then we have the Truffle slang interpreter with the bridge interpreted in Sulong. This is what we had at the end of phase 1, and it's clearly not something we can work with. Because we just implemented core control flow constructs and variables, we were constantly jumping back and forth over the native and Graal Java boundary. However, once we implemented specializations for doubles, we got back to roughly existing levels of performance for the interpreter. However, once we added, and I should preface this with, it's only an approximation of array specializations. The entire code can stay within Truffle. Slang functions can be inlined by the Graal JIT, and it can unroll groups and inline methods from, let's say, the add method from the list object. So the peak performance is pretty incredible here, but it's somewhat unrealistic, best case blue sky scenario. Here are our results for compiling certain parts of what we thought were what we suspected were the most used parts of the existing interpreter to LLVM bitcode. Immediately, you can see quite a big difference from having just the bridge in Sulong, and also that it improves upon the speed of the existing interpreter without any specializations. However, this comes with a downside, and that is knowing which libraries, which shared object files to compile is a dark art. And if you accidentally compile a library which makes even more use of the existing interpreter, you can degrade your performance. Compiling to LLVM bitcode piecemeal is hard. And if you miss subtle interactions, you can pay the price for them quite dearly. And even with this, specializations can have a negative effect on the performance. Actually, let me just come back to that. So you have in maroon, which is the first time we tried to compile parts of the existing interpreter to LLVM bitcode, and then in the kind of dark green beside it is the second time we tried it. The first library was a bit slower, and the second one was a bit faster, and the reason for this turned out to be quite subtle. So we implemented specializations on top of this again, and we found that, yes, they help improve performance in some cases, but not always. In this case, it actually made performance worse, and we had a few other benchmarks where it made performance worse as well. Now, why would this be the case? It's surprising, right? A specialization would remove a native interop call and remove the interop overhead. But it actually comes down to what specializations you implement. So think about the array example from earlier. If we have the result of size as a word size double, but we need to append that to an array which hasn't been specialized, then we need to allocate the memory to wrap that double back up into a DT value, send it across the native boundary, and have it be appended on the native interpreter side. In which case we're doing extra work, extra unnecessary work to unwrap and rewrap the double every single iteration of the loop. Our biggest win actually comes from using Substrate VM. That is compiling the Truffle Truffle slang interpreter to native code itself using Substrate's native function interface. The NFI is surprisingly low overhead, and from using just that alone, we were able to see a massive improvement in execution time. We think this comes down to the many optimizations you get almost for free with GraalVM. This includes function inlining, profiling, loop unrolling, and it also helps to have a very low overhead native interop. It gets even better when you implement specializations. However, the peak for, let's say, Sulong plus the double specialization plus the array, substrate plus the double specialization plus the array, doesn't seem to be as good as it is for, in the first case with GraalVM and just Sulong. This might be just one of those cases where a JIT compiler has more information at runtime and can produce better code than a ahead of time compilation can manage. So what have we just learned? We've seen how interop overhead is the main factor for figuring out which system is the fastest. If we had to rank them purely based on speed, we would do it as so. First, we'd say substrate VM. Next is compiling the existing interpreter to LLVM bitcode. And lastly is using GraalVM and Sulong for the bridge. However, we have to keep in mind that the peak performance of the last one was better than that of the first one. We've also seen that specializations are really useful for speeding things up, but they have their caveats. They can be difficult to get right. GraalVM with only double specializations but no array specializations spends an excessive amount of time unwrapping and rewrapping doubles for native interop. Another thing we found about specializations were they were quite insidious. What I mean by this is that adding a new type of values in the runtime requires you to update all the code which can be transitively reached by that value. And one thing that we found, which hasn't been too much of an issue to be fair, is that specializations don't support generics currently. So now we need to think about what the next steps are that we're taking based on these results. While it might seem like an obvious choice just to go with substrate VM, it's not without its downsides. It's overall more effort to develop with because you lose the JVM tooling, the build times increase, and you need to keep around 2 interfaces and duplicate your logic between substrate and Sulong. And there's no way to factor that out that we can see currently. And sticking with Sulong is really helpful and good, especially for debugging issues. It's just not great for performance and a production release right now. It would be great if we could compile our entire native C++ code base to LLVM bitcode and just let Sulong run with it. But right now that's not an option we have available. We use GCC and Visual Studio, and switching to Clang is on the roadmap, but not for now. So to make Sulong viable, we'd have to use specializations, and we've just seen that using specializations is generally useful, but it has its own downsides. And sometimes specializations can increase the complexity of a function multiplicatively. So if you have multiple arguments to a specialized function, then you need to think about all the cases of all the types for each function. The other reason that compiling to LLVM bitcode piecemeal, remember, is hard because you miss subtle interactions when you compile one library, but say not another few. We currently only have Truffle to native interop working. We still need to work on going the other way, that is, going from native to Truffle. Remember all those 10 million lines of C++ add-ins? We still need to make them work with Truffle nodes as opposed to our native nodes on the AST. We're thinking this should be possible, and we're hoping it's not going to be too fiddly. So wrapping up, we figured out the main answer to the remaining question from last time, which is, can we surpass the performance of the existing interpreter? I think we can fairly conclusively say, yes, we can. And we learned more lessons about using GraalVM. With respect to our evaluation from last time, first, we'd like to extend our gratitude to Oracle for supporting libc++. Originally, Truffle only supported libc++, but we didn't have Clang yet, so getting this far in this project would not have been possible without their help. We would also like to thank them for the improvements in the documentation. There were far fewer times that we needed to look at the implementations of, say, JavaScript, R, or Ruby, or Python to understand how to use Truffle or what a particular feature meant. On the other hand, there were a couple of things that we found difficult. One was the high overhead for using Sulog. This feels promising, but currently it's unsuitable for production deployment. It's good for debugging though. Another experience that we had that was slightly difficult was the tracing of errors between Graal and the native boundary. Sometimes you can make a programming error on the Java side, and that can end up causing a seg fault on the native side, and figuring out why that happened can be particularly tough. Sometimes you can get a frame without boxing error from compiled code, and kind of understand what it is about your interpreter that's doing that can be difficult. And we appreciate that having such tooling which could handle the jump between Java and native code would be really difficult, but it'd also be really useful. There were new lessons that we learned also with this phase 2 of our project. First was Substrate VM, surprisingly fast. It really makes the whole project way more feasible. The second one is the new library and export message API is really good. So this API allows you to separate the definition of and basic operations on a particular type from all the messages that that type can respond to. It very much helps with keeping code modular and keeping things high level. But there's a small downside to it, which is it can make code navigation quite tricky. You have to end up looking at generated code to understand what uses which part of which class and how these pieces fit together. So better code navigation would be ideal. Oops. The third thing is that specializations are generally useful to improve performance, but again, with the caveats that I mentioned earlier. Additionally, I think the reason that adding specializations can be a bit insidious is that it's an instance of the expression problem, so that'd be a tough problem to solve. However, one thing that's been somewhat unfortunate has been having to handle resource management. So this might be surprising initially, and it was surprising to us when we realized it. The whole premise of implementing a programming language in a garbage collected language like, say, Java, is that you don't need to worry about garbage collection. The runtime, in this case GraalVM, can take care of it for you. However, that assumes that everything that your language deals with is visible to and controllable by GraalVM, which is not the case when you're interoperating with an existing native code base which has its own rules and conventions about ownership and memory management. Even without the need to interoperate with native code, one thing that I stumbled across, and which was a bit of a surprise, was when I was trying to implement the array specialization for slang arrays in Java. Slang arrays have copy and write semantics. And to have these in our Truffle slang interpreter, we'd have to implement it manually. We would not be able to express it at the Java level, say in the same way that we could in a language like C++ or Rust. Truffle almost magically automates so many parts of implementing a fast language runtime that when we stumbled across this one, it was a bit of a surprise that even resource management wasn't automated away too. I have a kernel of an idea how you might be able to graft on some sort of linear type system with annotations onto Java, but we haven't really sat down and worked through it yet. Just before I finish, I'd like to say a very small side note. I'd like to see a Truffle, a Scala API for Truffle and Graal. That I think would be pretty interesting. Though some of my teammates are very at home with the object-oriented API, I personally come from a somewhat academic background. I'm used to things like GADTs and exhaustive pattern matching. And those features, I believe, would be really useful for things like enforcing which types you can store in the environment, which types you can have around at runtime, making sure that your specializations don't miss any cases. But yes, that's it. Thank you all for attending, especially when at one point I was doubting that even I wanted to attend my own talk with a talk on Pony and one by Philip Wadler in the other rooms. We're hiring, so we need senior engineers who are not afraid of digging into a 26-year-old code base. You can find out more online, gs.com/engineering, or you can email any one of us, first.last@gs.com. If you're interested in what I say and do personally, you can find a little plug for myself there, druvmakwana.com, links to my GitHub, LinkedIn. I have a YouTube channel called Atypical Komsky. I was trying to do educational videos on that and some general ramblings. If you're around for the full 5 days of curry on and eCoop, I'm also presenting a paper. It's called Linear Types for Linear Algebra. I wrote it with Dr. Neil Krishnaswamy, so please come check it out. And that's it. I got plenty of time for questions, so please do ask. No one wants to know about more about SecDB and slang? Yes.
I have a.
Hello.
Does it work? Yeah, and now it works. I have a quick question. So I was on the FastR team as we've discussed yesterday, so that brings a lot of bells in terms of like how badly the language is designed. But anyway, so you guys have started with a very, very low bar in the sense that Slack, as I understand, is interpreted and it's an IST interpreter. So have you, I know you considered a lot of options, but have you considered trying a better interpreter? I mean, that shouldn't be that difficult to do like a like a threading interpreter or something that's just not an AST interpreter. That should, like, that's what FastR, like that's what the original implementation of R has tried. I mean, they moved from an AST interpreter to a better and faster interpreter, and that helped quite a bit. So that's one question. I guess the other question is, because it seems like you're getting like really, really good performance results with Truffle and Graal. But did you try, just for the sake of it, to run sort of the Graal Truffle side without jitting, just to compare the performance of the interpreters on both sides? Probably not, but
so the first,
curious to know.
So the first question was, did we consider a better interpreter? Like, I assume you mean something like bytecode interpreter, at least. We have. The problem is that we have currently some add-ins which change the parse tree. So we figured that between rewriting the interpreter or trying to make it faster and just using GraalVM, which has this thing, it's right now the bet seems safer to make for Graal. If this doesn't pan out, which intuitively it feels unlikely, but it is something that we have considered. And the second one was about without the jitting. No, we have not tried it. That would be interesting, but in some sense, if it's like
it would be in any way useful for
you
guys, but it would be just, for me, it would be kind of useful to know what the how much the jitting actually.
Yes, it's a good question, and I think I'll run the numbers and we can definitely chat about that later. Yes, we have a question here.
My name is Fabio Niepaus, and I work on Smalltalk implementation in Truffle. So I was wondering, on slide 34 or something, you show your specializations. Why did you decide to return a double for the size of your array instead of using a long? Why is everything floating points?
Pardon?
Why do you use floating point arithmetic?
This was one of those design decisions that was made back in 1994.
Okay, so that's just in order to be compliant with the language.
That's exactly
it. Okay, second question.
Yes.
You're passing in a Java list.
Yes.
And that's an interface. Have you had a look at IGV graphs and make sure that this is actually going away and it's not using an invoke, causing an invoke?
We haven't had any reason to look at the IGV graphs because the performance was fairly good once we had a look at it.
I would encourage you to have a look because there might be some easy tricks that you can pull off here to make it even faster. Sure.
The main problem with lists and arrays right now was actually getting the copy and write semantics. So this was, like I said, it was a prototype implementation I hacked up just to see kind of blue skies numbers. We have a question back here.
Yeah, all the time. Sorry,
Oh.